It's good to be aware of some common big O time complexities that you'll likely face, as well as the colloquial names that we give them when we talk about them. So the smallest time complexity that you'll face is big O of 1. So we call this constant time. So big O of 1 is constant time. It means that your algorithm does not depend, the time complexity of your algorithm does not depend on the input size. It doesn't matter if you have 10 elements versus a million elements, it will take just as long to run your algorithm. Next, you'll likely see big O of log n, which we call logarithmic time. Or I'll just call it logarithmic. So logarithmic time, if I double my input size, I would increase the number of operations by a constant, for example, by 1. So one common logarithmic time algorithm that you've probably seen is binary search. With binary search, if I have 8 elements, it'll take me 3 operations to perform my algorithm. If I double it and have 16 elements, all that'll do is add a single additional check that I have to do. So if I double my input size, or in general multiply by my input size by some constant, I would increase the number of operations by some constant. And note that I didn't list log base 2 or base anything of n. And the reason for this is because I can convert between any logarithm base by multiplying by a constant scaling factor. And because big O notation drops constant coefficients, it doesn't matter what base your logarithm is in. Whatever base you listed in is some constant times any other arbitrary base. So usually you'll write it without a base if it's in big O notation. We also have big O of n, which is called linear time. So your algorithm scales linearly with respect to the input size. If I double my input size, I would double roughly the number of operations I perform. So twice as big means roughly twice as slow. We have big O of n log n that I don't think has a super clean colloquial name, so I'll just keep it as big O of n log n. But some common big O of n log n algorithms that you might see are like merge sort or any of the other fast sorting algorithms. They scale basically linear logarithmically, so n times log n as a function of the input size. We also have big O of n squared, which we call quadratic time. So if I double my input size, I quadruple the amount of operations I have to perform. So for example, if you do some all pairwise distances computation of some sort, or every single pair of elements comparison, there's usually n squared, big O of n squared pairwise elements. So that would be quadratic. Big O of n cubed, we would call this cubic. So similar to big O of n squared, if I double my input size, I would multiply my number of operations by 8. It scales cubically. And generally speaking, all of these, whoops, that's not pretty. All of these, or in general, anything that is upper bounded by big O of n to some constant for any constant c, we call polynomial time. So constant time is polynomial time. N to the 0 is an upper bound on this. Logarithmic time is polynomial time because big O of n to the 1 is an upper bound on big O of log n. Big O of n is just big O of n to the 1. N log n is also polynomial because big O of n to the 2 is larger than big O of n log n, and so on and so forth. So anything that is upper bounded by big O of n to some constant is called polynomial, even if it already has another one of these names. Generally, polynomial time algorithms are considered quote-unquote good, versus we have some quote-unquote bad time complexities, such as big O of k to the n for some constant k. This is called exponential time, or exponential. For example, you might see big O of 2 to the n, or big O of 3 to the n. As n increases, n being the input size, this scales pretty horribly. So in bioinformatics, one example is the sequence alignment problem. To optimally solve that problem, if I have n sequences of length k, this is big O of k to the n to solve. Another bad one is factorial time. So this is big O of n factorial, which is factorial time. So in factorial, this is n times n minus 1 times n minus 2, so on and so forth. So things that are not polynomial, even for relatively small values of n, become extremely slow.